In this paper, we propose Jabbic lookups, which is a telemetry-based system for malware triage at the interface between proprietary reputation score systems and malware analysts. Jabbic uses a file download telemetry collected from client protection solutions installed on end hosts to determine the threat level of an unknown file based on telemetry data associated with files already known to be malign. We show that Jabbic can leverage file download telemetry to allow security vendors to manage the collection and analysis of unknown files from remote end hosts for timely processing by more sophisticated malware analysis systems. Jabbic is positioned at the interface between a proprietary reputation score system, which is widely used by security companies to flag potentially malicious files using telemetry data, and the malware analysts who decide whether files should be submitted for further analysis, exactly how we show in the figure in the current slide. When a file is downloaded, the antivirus software sends telemetry data to a reputation score system that is proprietary to the vendor. Then, the telemetry data of unknown files with negative reputation scores are forwarded to Jabbic, which then searches for non-malicious files whose telemetry data are similar both semantically and relationally to that of the unknown files. The unknown and non-malicious files, their reputation scores, and the confidence score with which Jabbic matched them are sent to the malware analyst, who then decides whether to initiate a file collection request to the end host. As we will later show in this presentation, the confidence score quantifies the likelihood that an unknown file and a known malicious file found by Jabbic share the same malware family. Now, we found that file risk levels based on reputation scores are not necessarily representative of how malicious they are. For example, if you look at the table in the current slide, the unknown and known files with the same malware family have a very large discrepancy in their risk levels, despite performing similar malicious activities. So we expected that if two files with the same malware family had similar scores, since they perform similar malicious activities, but that's not always the case. So for this reason, we propose that the triage process is based on the Jabbic score once files are flagged as suspicious by the reputation score system, rather than triaging them purely based on the reputation scores. In terms of data, we leveraged a dataset from NortonLifelock's data sharing platform. The dataset contains information on over 33 million download events for the entire month of October 2015, and include the hash string of the downloaded file, the hash string of the parent file that initiated the download, the IP of the file host, the URL of the file host, and the time and date the file was first observed by NortonLifelock. The data also includes the file reputation scores denoting low, medium, and high risk levels. We also augmented this data set with autonomous system information. The autonomous system number for each download IP was identified using the IP to autonomous system mappings published on University of Oregon Root Views archive, also cited in the paper. Lastly, we obtained malware families for query files and their matches from virus total reports. In terms of methods, our approach is mostly based on word embeddings, in particular word2vec, which is an approach which can be applied to data, which is structured as a sequence of words, typically formed into sentences. Now, unlike natural language, in which words are linked by semantics and sentences arise naturally, in order to apply it in the present context, we need to artificially formulate a sentence-like representation of the file download information. So what we did was to conceptualize a download event as a structured fragment of information of the form: an autonomous system that owned an IP address facilitated the download of a file from a domain at a particular location given by the URL path. So each download event is therefore represented as a sequence of words as follows: autonomous system, network ID, host ID, file hash, domain, URL, path, before being fed to the word2vec model for training. Now, to identify matches for a given input file, which is the unknown file that we don't know whether or not it is malicious, we adopt a search method developed by Zhang et al. That finds terms in the previous time slices that are semantically closest to a given input term in the present time slice. So the method of Zhang et al. Was designed specifically for querying archives and collections of past documents, but we've adapted it to our own context. This method uses both semantic and relational similarities to find files that are siblings by delivery infrastructure. Relational similarity is the correspondence between relations, in contrast with semantic similarity, which is a correspondence between attributes. When two words have a high degree of semantic similarity, then they are called synonyms. When two pairs of words have a high degree of relational similarity, we say that their relations are analogous. For example, the word pair, carpenter and wood, is analogous to word pair, chef and dinner. So these words are not synonyms, but instead they are analogous from a relational perspective. The Radcliffe-Oberschelp or RO pattern matching algorithm compares two strings and outputs a value between 0 and 1, where 1 denotes a complete match between the two strings and 0 indicates no strings in common. So in our context, we use this algorithm, the RO score, to quantify the overlap between the contextual information of pairs of query and match files in a string-like sense. So for example, this measures the similarity between the context of two files, which we use as a confidence measure that allows us to quantify the certainty with which Jabbic can associate a local match file with a given query file. On this slide, we present the Jabbic lookups architecture. Before we discussing the details of the architecture, we would like to introduce two main terms in here. The first one is the base vector space, and the second one is the target vector space. We refer to as the base vector space a vector-based model which was trained on telemetry data associated with files which have not been previously seen. In our case, the query files, for which we are trying to find a match in any of the previous days or any in the previous time slices. A target vector space, on the other hand, is a vector-based model trained on telemetry data associated with files already known to be malicious. That is, the vector space which contains those files where we are searching for matches given as input a query or unknown file. So the system architecture is illustrated in the current figure. So first, we determine the temporal granularity by which telemetry data from known malicious files is to be split. For example, in our case, by day. 2, we train separate target vector-based models for each day, and then we store them into a lookup database. This allows us for the selection of a specific past time frame within which searching for a local match is carried out. 3, we train a base vector space for the day which contains the query files, that is, those files that have not been downloaded in any previous time frames. 4, we select a target vector space within which local matches are to be searched given the query files from the base vector-based model. For example, given query files downloaded on 31st of October 2015, find their best local matches among files downloaded on 1st of October 2015. 5, we need to align the base and target vector spaces to a common vector space in which cosine similarities can be computed. 6, we identify query files as those files that have not been seen before. At step 7, for each query file in the base vector space, we find its most representative match file in target vector space from a previous time frame, and then assess the confidence with which these files are matched using the RO score. After lookups are completed, the current base vector space can then be added to the lookup database, which can then be queried when local matches are searched for queries downloaded the next day. In order to set the confidence RO score threshold, we identified over 100,000 unique hashes of files downloaded only on 31st of October 2015 to ensure that no prior information about these files was known to Jabbic in the lookup process. For each of these files, Jabbic lookups are used to search their match file hashes in every previous day. So what we found was that over 87% of query match pairs with RO scores in range 0.6 to 1 had the same mother family. Thus, for any given query match pair, a higher RO score increases the probability that the mother family of query files is the same as that of its match. Now, for a second stage triage, we aim for the highest true positive rate. So that means we want to identify as many queries as possible that have the same mother families as their matches, while accepting a higher false positive rate, since the cost of collecting and analyzing mismatched unknown files has no significant practical implications. The initial triage of files as either benign or potentially malign has already been done by the reputation score system. Therefore, the only implication of Jabbic matching a small proportion of unknown files to malicious known files with different mother families is that the unknown files are collected and analyzed earlier than they otherwise would. So for this reason, we accept the confidence RO score threshold of 0.6 as optimal, which not only correctly matches the highest proportion of unknown query files to known malicious files by mother families, but also achieves the lowest false positive rate. Now, we have previously mentioned that the RO scores of local matching provide a measure of the confidence associated with the triage of a given query file. On this basis, the over 100,000 query files which we identified, downloaded solely on 31st of October 2015, can be triaged with very high confidence based on files downloaded up to 7 days before, as we can also see in the figure in the current slide. We also recommend that the confidence with which a query and the match file are paired by malware family is evaluated based on the following confidence levels. So a high confidence level if the RO score is in between 0.6 and 1, or we cannot tell whether or not they share the same mother family if the RO score is lower than 0.6. We have previously mentioned that we found that file reputation scores are not consistent across files belonging to the same mother families. So for example, we identified over 600 files with mother family Zusi, which had reputation scores denoting low, medium, and high levels of risk. And this is very interesting since these files perform similar malicious activities. We would not expect that we have such a wide range of reputation scores. In the figure in the current slide, we illustrate the prioritization of files using the reputation score system and Jabbic. So query files sorted in ascending order by the reputation scores are matched with non-malicious files whose reputation scores do not reflect similar levels of maliciousness despite being very likely to have the same mother family. And we show this in heat maps A and B. So most notably, query files with the lowest priority would have been prioritized for collection and analysis much earlier, judging by the risk levels of their match files. Similarly, most of query files with highest priority for collection and analysis are matched with known files having much lower priority. So again, heat maps A and B indicate that we have already shown, and that is that query match pairs have significantly different levels of risk despite belonging to the same mother families. Therefore, we propose that file reputation scores are at most reliable for an initial triage of unknown files as either potentially malign or benign, but not for further prioritization of malign files. So in heat map C and D, we show that query files are sorted in descending order by the confidence arrow scores with which Jabbic paired them with known malicious files, and which would allow us to perform a much better prioritization of these files rather than using just the reputation scores. We have also compared our method with VirusTotal and a number of variant baselines. So VirusTotal reports both the date when a file was submitted for the analysis and the date it was detected as malign. We find that more than half of the query files found as malicious on VirusTotal were detected over 20 days after they were submitted for scanning. So Jabbic could thus have triaged and flagged as suspicious over half of the query files in less than a day, if not hours, depending on the search space size. We also compared the performance of Jabbic with the skipgram, SIBO, FastText, TF-IDF, Bloom filters, and locality sensitivity hashing, which are commonly used in malware detection systems based on string level similarity of opcodes, network packets, download payloads, application programming interface, method calls, instruction sequences, and binary strings. The overall performance of Jabbic not only surpassed that of all the baseline methods, but was also much faster than those whose performance was relatively close, particularly set-based matching with locality sensitive hashing and Bloom filters, which took over 10 days to run, when compared to Jabbic, which took around 5 hours, for example. Now, in terms of system performance, training word-to-vec models for each day was carried out on a home machine using 5 CPU cores with 2 worker threads per core. The lookup process was carried out in batches of 1,500 query file hashes, required 1 CPU core, and approximately 140 gigabytes of RAM. The average training and search times are shown in the table in the current slide. So the lookup time is expected to scale approximately linearly with the number of unique files in the search space. The search time of all of the query files, that is over 100,000, in a sample of over 1 million download events, took close to 5 hours. So even an order of magnitude increase should still produce results on useful timescales. And this could further be mitigated by the use of multiple machines or cores. Now, in terms of Jabbic limitations, we identified that perhaps the main problem here is that Jabbic lookups rely on the alignment of one vector space to the other, which requires that some file hashes are found in both vector spaces. So that means they were downloaded across multiple days, or at least across two days. If no file hashes are common to both vector spaces, then the alignment of one vector space to another is not possible. However, we found that a sufficiently high number of file hashes were downloaded not only from one day to another, but also across multiple days. Thereby, the alignment of vector spaces should not pose any issues in similar analyses. Thank you for listening.